Welcome to the Dynamic World session at Geo4Good 2020. I'm Tanya Birch from the Google Earth Outreach team, and I'm excited to kick off our session today. We're joined today by our partners Steve Brumby of National Geographic Society and Craig Hansen from the World Resources Institute and Chris Brown from Google. We've teamed up on a project called Dynamic World, which is an ambitious project to produce a 10-meter resolution global land cover map using modern neural networks. We're going to hear from Steve on what is the state of the art of land cover and why we need a map like Dynamic World and how to build a training data set for modern machine learning models. Chris is going to say how we can build neural networks and some of the science innovations we've made along the way. And finally, Craig is going to say why this is important for people, for biodiversity, and for climate. At the 2018 Geo4Good, Chief Scientist of National Geographic Society, Jonathan Bailey, announced a partnership with Google to explore technologies to protect nature and advance our scientific understanding of how to protect, manage, and restore enough nature for humanity to thrive. So we're excited today to share some of the results of this project 2 years in the making, called Dynamic World. Now I'm going to turn it over to Steve Brumby.
Thank you, Tanya. I'm Steve Brumby at National Geographic Society. World leaders seeking a path to a greener, more inclusive and sustainable future need a new type of map, a dynamic map of the world that can be updated automatically and continuously, that can inform decision-making about what and where we protect, restore and manage, and that can reveal the impact of our actions. At National Geographic Society, we're trying to help countries all around the world meet their obligations to the big international conventions on climate change and biodiversity preservation and all the UN sustainability goals. And as countries try and address these multiple conventions, it comes down really to three things. Where do you protect? Where do you restore? And where do you manage? Your environment, your agricultural land, your settlements, coastal regions and marine and everything else. And to do that type of planning, you need a map. Now, the best available maps for the world look like this. These are the European Space Agency CCI maps, and they have a resolution of 300 meters per pixel, which looks great at global scale, but as you zoom in on a country, they become very blocky and they have limitations on enabling the type of planning that the countries need. In the United States, we're fortunate to have a much higher resolution set of maps made by the US Geological Survey at 30 meters per pixel, made from the Landsat satellites. And these are really good, but this type of map is not available for almost all of the world. Now, in the last 5 years, there is a new type of satellite data produced by the European Space Agency from the Sentinel-2 satellites that's publicly available, and all of it happens to be already in commercial cloud, for example, on Google Earth Engine. And the question is, why aren't we making maps with this type of data right now? To make a map of the world at 10 meters per pixel, there aren't enough humans to make these maps. You need to use machine learning and artificial intelligence to produce these maps. And to make the computer make the map, to teach the computer to make the map, you need to teach the computer what it is you want to map. So we've replaced the task of programming the computer to make the map with the task of providing enough examples to the computer so that the computer can program itself. So the bottleneck has been, to date, the existence of a large enough training data set that can help the machine learn to make the map we need. To make the training labels, you also need to have a very good idea about what you're trying to map. So our colleagues at World Resources Institute actually helped come up with a list of the words we want to use to label the world, more formally a hierarchical taxonomy of land use and land cover types. And we've been focused for the current work over the last 2 years on what we call the Tier 1 categories, basic land cover categories, which have just never been mapped over the world surface at 10 meters per pixel. From that taxonomy, you now need to sample from the world surface, and you want to do this sampling across all the continents and across all the major types of land cover so that the machine has got the best chance to generalize. And you want to do this not just with hundreds of sites or even with thousands of sites, but actually with tens of thousands of sites. And so we at National Geographic Society, we recruited a cohort of human experts and others who have looked at these tens of thousands of sites, have used tools to mark up not just individual pixels, but blocks of continuous pixels and what's called dense markup. And so we can take these tens of thousands of tiles across all the world and produce tens of thousands of label images. And in fact, by doing this, we've produced, for the first time ever, we've produced a training data set of over 5 billion human labeled pixels. To the best of our knowledge, this data set is 10,000 times bigger than the previously available best training data set. And so from that, we can do a couple of things. One thing we can do is we can actually compare how well humans can do this task of labeling the Earth from satellite imagery. And in a forthcoming science paper, we're going to have some very interesting statistics measuring the accuracy of humans, both experts and also crowds of humans in this type of labeling task. And by taking all these billions of pixels, we're now able to turn maps like this, which is the current European Space Agency map for Costa Rica, turn it into something that looks like this at 10-meter resolution, which is now a really interesting spatial resolution to support spatial planning by country governments and international organizations. So to talk about that hard bit of how do you go from all these pixels into the machine learning algorithm that can make these maps, I now turn it over to my colleague.
Thank you, Steve. I'm Chris Brown. I'm with Google. And to bounce right off of what Steve was talking about, let's talk a little bit about how we actually teach a machine to take images of the world and turn them into this taxonomic breakdown, as shown by Steve in Tier 1. The next slide. I'm sorry, on the next slide, if you could advance for me, thank you. We can actually start to leverage modern machine learning to do this type of analysis. Previously, if you would have needed multiple images, a time series, sensor fusion, all of these make the process of scaling your algorithm and training it much more difficult. But now that we can lean into technologies like TensorFlow and modern machine learning, this starts to be something we can do where we can take one of these 10-meter per pixel acquisitions from the Sentinel satellites and produce a map. So if you go to the next slide, please. So we're also being conscious about exactly how we're building this model. So we're using modern machine learning powered by TensorFlow. But as you know, or may have heard, this can be a very expensive process. A lot of models that are commonly used for segmentation or making thematic maps from satellite imagery, if you check the literature, you'll see things like UNet, you'll see things like DeepLab. Dynamic World, the model we're using, is actually 20 times smaller than UNet and 200 times smaller than DeepLab, meaning both the energy footprint of the model to run inference is much less and the cost of training is much less. And this is was found during some analysis we performed to actually derive an architecture that was optimal for this this type of task. Go to the next slide, please. So another technique we're applying here is looking beyond just producing a land cover map. How can we inform the model beyond just the labels we have? Human annotators, it's amazing what a human can do when they look at an image of the Earth, but they can make mistakes too. And when you're in a time crunch, maybe you miss a road here, maybe you miss a tree there. So we can actually have the machine teach itself to recover a map that not only matches what our labelers will produce, but also matches what the Earth should have looked like when that map was made. So the model is actually trained to be bidirectional. It both creates a land cover map and then creates a reverse land cover map. The next slide, please. So there's actually something really powerful we can do when we're using modern machine learning techniques, because not only are we able to get this sort of taxonomic breakdown, but we can get a continuous breakdown. So I have a short demo here. And what we're actually looking at is that continuous breakdown. This is what the true output of dynamic world looks like, of course, you can recover a taxonomy like a standard land cover map, as Steve showed, but we can also see the mixture. At every pixel is some combination of trees or ag or scrub. It's really complex, and we can start to describe the surface of the earth in much greater detail than we could with just a single label. And we can actually go beyond this. If we actually apply some derived analysis on top of dynamic world's mixture of object type or land cover type, we can actually derive new insights. So what I'll show here is, in fact, using a collection of 60 points, we trained a very simple linear classifier to identify wheat fields and walnut fields so this is the Central Valley in California. This runs interactively, and this is done purely off of the mixtures produced by Dynamic World in its taxonomic breakdown. And of course, this is great if you just talk about it, but is it actually working? Is it actually any good? So I'll say it now, this is a very preliminary result, but based on our 3 expert agreement metric, which is the most rigorous agreement between our expert annotators, currently we're getting something like 85% accurate across our all of our classes. And so finally, we can talk about scaling this thing. So what's pretty amazing about using modern machine learning and not requiring multiple input sources and sensor fusion and time series and all these things we talked about is we can now lean into the power of commercial cloud AI platform to run the inference in an incredibly parallel way. For every sentinel image now, when we want to produce a map, we can turn that image directly into a land cover map. And going into the future, one could even imagine that we could apply this to every incoming Sentinel image. And finally here, we can start to see all of these things put together. You got a little teaser from Steve earlier, but here, when we're looking at New Zealand, we can see both a map of this taxonomic breakdown done by Dynamic World. We can also see these confidences, this mixture in the most confident class used to produce this actual hillshade, this topographic visualization. So you can see it all coming together in all of the rich inputs you actually get when making decisions based off of Dynamic World. So to discuss why any of this is useful, I'd like to hand it over to Craig Hansen from WRI.
Thank you, Chris. So there you have it, Dynamic World. It's not only new, but also extremely important. It's important for people. Next year, nations of the world will gather for the first Food Systems Summit, which aims to figure out how we will feed ourselves over the coming years in a manner that doesn't destroy the planet in the process. They will need to know where food is being grown and how productive fields are. They will need to know where prime cropland is being lost to suburban sprawl and natural disasters. They will need to be able to plan growth more wisely to balance food and other demands. Dynamic World can help make that a reality. It's important for biodiversity. Next year, nations of the world will gather in China to agree to targets to save the world's biodiversity and stave off the planet's 6th great extinction. They will need to know where the ecosystems that support this biodiversity are located. They'll need to know where to expand parks and protected areas. They'll need to know where and when illegal clearing occurs. Dynamic World can be an essential tool for doing that. It's important for climate. Next year, nations of the world will gather in Scotland to agree upon next steps in the global fight against climate change. WRI enjoys a wonderful partnership with Google on Global Forest Watch, monitoring the Earth's forests in near real time. What Dynamic World will do is help us go beyond forests. This is needed because carbon is found in grasslands, wetlands, croplands, and other ecosystems too. So as countries prepare their nationally determined contributions to support the Paris Agreement on climate change, they need to know exactly where their ecosystems are, what is happening to them, and what the implications are for climate. Today, this is hard, if not impossible. Our vision is that soon you can do it, making nature-based solutions for climate a reality. The next decade may very well be make or break for people on the planet. If there is to be any hope of us emerging out the other side intact, we need every piece of information about the planet and what we're doing to it at our fingertips. Dynamic World will help us get there. Thank you.
Thank you very much to our speakers today, and please stay tuned for more updates to Dynamic World on our Medium channel, Twitter, and Facebook.